Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 8, Exploring the Symmetry in Graphs of Quadratic Functions. Okay, classwork, graphing vocabulary. So we're going to go over some vocabulary before we get started. Vocab, axes of symmetry. Symmetry just means that if something is symmetrical, then what happens to the right is going to be mirrored on the left across that line of symmetry or axis of symmetry. So it says, given a quadratic function in standard form, f of x, and for all of you, f of x is the same as y. What that means is when x is a certain number, y is what? And I'll lead up to that soon. So f of x equals ax squared plus bx plus c, standard form. The vertical line given by the graph of the equation x equals negative b divided by 2 times a is called the axis of symmetry of the graph of the quadratic function. Very important that you know this. Okay, you need to memorize that. X equals negative b over 2a. So whatever b is, you take its negative and divide it by 2 times whatever a is. And that will tell you this point, this x value, or I'm sorry, yeah, the x value, x equals is a vertical line. X equals, in this case, would be 3. So when x is 3, y is 0. When x is 3, y is 1. When x is 3, y is 2. X is always 3, so it's just x equals 3 in this example here. Okay, vertex. Now moving on to vertex. The vertex is the point where the graph of the quadratic function and its axis of symmetry intersect. Okay, so the axis of symmetry, which is found by taking negative b over 2a, finding this line here, but then when you take that x value and plug it in or substitute it into this equation and you find a y value, then that x comma y value is this point right here called the vertex, which is the minimum value of this function, or if it was flipped over, it'd be the maximum value of the function. Okay, moving on, end behavior. The end behavior of the graph, they're talking about what's going on at the ends. Well, this is a continuing function. It goes on forever and ever and ever. So what you really do is say, if you got this little dude standing here, okay, here's this little dude. I don't know if you guys know the song Walk This Way by Aerosmith. So this is Steve Tyler. He's up on stage. I think you know him from a TV show more so than his band these days. But as Steve Tyler walks this way, does he have to look up or does he have to look down from the stage to see where the graph is going? That is end behavior. So as I'm going to call Steve Tyler x, as x goes to the right, which is positive infinity, as Steve goes to the right, does he have to look up or does he have to look down? Okay. If he looks up, like in this case, then y is approaching, that's what that arrow means, y is approaching positive infinity. Okay, so now, if I ask Steve, go to the left. If Steve walks this way, then as Steve goes to the left, which is negative infinity, as x approaches negative infinity, does Steve have to look up or does Steve have to look down? So if Steve here is over here now, does he have to look up to see the end of the graph or does he have to look down? Well, he has to look up. So as Steve goes to the left, negative infinity, Steve has to look up, which is positive infinity. And that's really end behavior. It's really that easy if you think of it this way. So as you go to the right, you have to look up or down, and as you go to the left, you have to look up or down. That's end behavior. And we will practice that in this lesson. Okay, so exploratory challenge. Here's some pictures. Okay, the St. Louis Arch in St. Louis, Missouri. Bellows Falls Arch Bridge. Not sure where that is. Arch of Constantine. Do you know where that is? And the Roman Aqueduct. Okay, so below are some examples of curves found in architecture around the world. Some of these might be represented by graphs of quadratic functions. What are the key features these curves have in common with a graph of quadratic functions? Well, if you look, the arch is going up, it reaches a maximum point, and it mirrors. So this distance from here to here would be the same as this distance from here to here. And same goes for this. This arch, obviously, we're looking at it at an angle, so it doesn't appear to be symmetrical, but if we were on a boat in the water, then we would see that at this point right here, the distance from here to here and the distance from there to there is equal. Okay, the arch of Constantine, if we did this, and then the vertex would be through the middle here. So if we were standing right in the middle of this arch, we would be the same distance from the left wall as we would be the right wall. And same goes for this aqueduct. Okay, so if we were in this one, the distance from here to here is the same as here to here. Okay, so they all look like parabolas. They are, and that's what a graph of a quadratic is called, a parabola. Parabola. Okay, and they're all opening down. They have a maximum height. Okay, and if they went to infinity, they would keep going underground, if you will. They would keep getting further and further apart. The photographs of architectural features above might be closely represented by graphs of quadratic functions. Answer the following questions based on the pictures. A, how would you describe the overall shape of the graph of the quadratic function? Okay, you might just say it's a curve or an arch. Okay, since that's why we're calling that an arch. Okay, but it is called a parabola. Okay, another way we could say this is it's probably U-shaped, but it's an upside down U in this case. Sometimes parabolas look like that. So it's U-shaped or arch, okay? B says, what is similar or different about overall shape of the above curves? Well, what is similar? Well, they all have a maximum. They all have a height where they reach the top and then turn and go back down. What else do they have in similar that is similar? They all are U-shaped upside down. They all have the highest point. That was the maximum. And what's the difference? Well, this arch here actually curves, and if we look at it, it looks like the walls are straight for a while, and then it curves, and then comes straight down. So those aren't curving out like a parabola would, going out this way. So this arch is different than these. These look like they keep spreading wider and wider. Same with the St. Louis arch, looks like it's possibly straightening out as well. And these probably are the same as well, but this looks like it keeps curving. Okay, so those are some differences. Exploratory challenge 2. Use the graph of the quadratic functions, graph A and graph B, to fill in the table and answer the questions on the following page. So here's graph A, and here's a table. So at -1, so that's right here, we have to go up, and that is the point 8. So -1, 8 is right here. Then we jump over to 2, -1. So we went over to 2, and we had to go down to 1, and there's our point right there. And what is that called? That is the vertex. That is the lowest point on the graph. And the x value of the vertex is the axis of symmetry. So the axis of symmetry is x equals our x value, 2. So if I drew a vertical line right here, that is our axis of symmetry. So every point, this is 1, 2 units from the axis of symmetry. This is 1, 2 units from the axis of symmetry. And 8 is 1, 2, 3. Therefore, 1, 2, 3. And we're at this point, which is 5, 8. So I'm going to put that in there, 5, 8. We have 4, 3 here. So I go over to this side, and that is 0, 3. So that would probably go here. Okay, so we have a y value of 8, we have a y value of 8. We have a y value of 3, we have a y value of 3. This is our vertex. So what other point do we have in between? And I see that we're looking for integer values, by the way. So there's the point 1, 0. So that's going to go here. -1, 0, 1, 0. And I see a pattern here. So whenever we have a parabola, the y values going away from the vertex generally they match. When we go with the same number of units of x values, the y value will be equal. So this is probably 3. So if I come over here, sure enough, there's the point 3 comma 0, and our zeros match. So it's a mirror image around the vertex or the axis of symmetry. Okay, so try graph B, pause the video, see if you can do this, and then come back. Okay, assuming that you've done this now, I am just going to continue, and it has the point -2, then -3. So I'm going to go up this way, and I'm going to go until I find the next integer, and it's -4. So I'm going to write -4 there, and I'm going to continue down until I find another integer, and that is right here on the corner of the grid, which is x -5. Okay, so what is the y value at -5? It is -5. So we go left 5, down 5. That is the point -5, -5. This is the point -4, 0. And then as I go to the right, I have this point here. That's an integer. I continue until I'm at this point here. That's an integer. On a line, on a line, on a line, on a line, on a corner. So there's my 3 integers. They gave us -1 or 1 -5. So I'm looking at -5, -4, -3, -2, -1, 0, 1. And sure enough, -1 is here, 0 is here. What's the y value at -1? 3. What's the y value at 0? 0. It's the origin. So my vertex is my maximum point at the top here. There's my vertex, -2, 4. And since that's the vertex, the axis of symmetry, which is right down, straight down the middle here, is x equals my x value, -2. That's my axis of symmetry. On either side of that axis of symmetry, your y values match. 0, 0, -5, -5. Now it says use your graphs and tables of values from the previous page to fill in the blanks or answer the questions for each below. Okay, so rather than going back and forth from the last page to this page, I have copied over graph A and the table A, and we're going to answer graph A questions first, and then we'll go back and do the others. Okay, so it says 1, what is the x-intercept? That means where does it cross the x-axis? So here's the x-axis right here, and it crosses at x equals 1 and x equals 3. So that is the point 1, 0 and 3, 0. Okay, those are those 2 points, axis, or those are the x-intercepts. The vertex we already answered previously. It's the point 2, -1. That is this vertical line right here. Difficult drawing a straight line. That's x equals 2. So that would be, and when x equals 2, the vertex is this point here on the axis of symmetry, the intersection where the axis of symmetry intersects the parabola. So it's 2, -1. 3, sign of the leading coefficient. We haven't discussed this yet. So remember the formula is f of x equals ax squared plus bx plus c. So when a is positive, when the leading term here is a positive number, the parabola is going to open up. When a is negative, when this term here is negative, the parabola is going to open down, like that. Okay, so now answer this question. What is the sign of leading coefficient? Which way is this opening? It's opening up like this, so A is positive. Vertex represents a minimum or maximum. Well, when it's opening up, this is a minimum. Okay, so when the leading coefficient is positive, the function has a minimum. When the leading coefficient is negative, the function has a maximum. Points of symmetry. Find f of -1 and f of 5. So here is my function that I talked about. This is called our function f of x, and I said f of x is the same as y. And what it means is, how I would say this is, what is y when x is -1? What is y when? So that's what f means. What is y when? What is y when x is 5? What is y when x is -1? So f of -1 is, what is y when x is -1? Well, it's right here. And no, it's not. It's right up here. Sorry, right here. And f of -1 is 8. What is y when f is 5? When x is 5. So x is 5 here. We need to go up to this point right here, and that is also 8. Is f of 7 greater than or less than 8? What they mean is, when x is 7, is y greater than or less than 8? So if I went out to here, 7, well, am I going to be above or below this line right here? Well, obviously it's going to continue up. It will be greater than. So I would say f of 7 is greater than 8. And as you can see, there's the line y equals 8. F of 7 cannot turn and come back down. Parabolas never turn and go the other way like that. Never. They always continue in this direction forever and ever. And that's why f of 7 has to be greater than 8. Okay, number 6. Increasing or decreasing intervals. Now we're talking about intervals. What's an interval? An interval means between a certain x value, two x values, what is the function doing? Okay, so it says increasing and decreasing intervals. On what intervals of the domain? Domain is x. On what intervals along the x-axis is the function depicted by the graph increasing? So if I were to draw this line, am I going up or down right now? This is going down, so that's decreasing. When we get to the axis of symmetry vertex point, we turn and we start to go up, and that's an increasing. So on what intervals of the domain is the function depicted by the graph increasing? Well, it's increasing from here to infinity. So that is the point x is 2. So we use a parentheses here because it's not increasing at the point, so we can't use a bracket. So if it's also increasing at that point, you would use this. Okay, but in our situation, it's not increasing at 2, it's increasing from the open interval 2 to positive infinity. So it's increasing from here to the right forever and ever and ever. On what intervals of the domain is the function depicted by the graph decreasing? Okay, well, decreasing is when the function is going down, 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 and it does that until it gets to 2. So it stops decreasing at 2, so that's my last point. But it decreases from negative infinity all the way down to 2. So those are the intervals of increase and decrease. Average rate of change on an interval. What is the average rate of change for the following intervals? -1 to 0, 0 to 1, 0 to 3, and 1 to 3. So we're doing different intervals now. Let me erase my values here. Okay, average rate of change. The easiest way for me to explain this is over an interval from -1 to 0. These are x values, by the way. So what is x at -1? The x at -1 is 8. That's right here. So that's the point -1, 8, which is right here. And this is the point 0, 3, which is right here. So 0, 3 is right here. So they want to know what the average rate of change is from this point here to this point here. Okay, so, well, average rate of change is like a linear function. So if I got my ruler out, and I put it right on this point here and rotate it through this point, as accurate as possible, then what I'm asking is what is the slope of that line? That's basically average rate of change between 2 points. So I went down 1, 2, 3, 4, 5 over 1, so my average rate of change is -5. If I were to show my work on that, I'd say average rate of change is y2 minus y1 divided by x2 minus x1, which is my slope. So if I plug these values in, y2 is 3 minus y1, which is 8, divided by x2, which is 0, minus x1, which is -1. So minus and negative is +1, so be careful with that. And 3 minus 8 is -5. And 0 plus 1 is 1, and -5 over 1 is -5. Okay, hopefully that makes sense to you. That's just a basic way of doing it. There is also another, oh, I didn't want to erase that. There's also another formula later in math, probably calculus, but we're not there yet, so don't worry about it. All right, so next thing we want to do is find the interval. That's supposed to be a 5 there, 0 to 1. So here is the interval from x is 0, this point here, to this point here. So from 0, 3, which is here, to 1, 0, which is here, what's the slope? Well, I went down 1, 2, 3 over 1. That would be -3. I'm just doing this quickly. Okay, and now I have the from 0 to 3. So now I'm talking about this point, but now I'm moving to this point. So now I'm moving my point from 0, 3 to 3, 0. Okay, so what's the average rate of change here? Well, can I just draw a line from here to here and find the slope and say it's down 3 over 3, which is -1? Okay, just like that. Average rate of change is -1. It's an average, remember. It's decreasing faster here, but then it's increasing. You add all the negative values up to the positive, and you end up with a -1, basically. All right, next one. This is from interval 1, x is 1, to x is 3. Okay, well, that's a horizontal line, and what the slope is, and if I want to use the points from 1 to 3, it'd be y2 minus y1. Let me just do that. y2 minus y1 over x minus y1 over x1, x2 minus x1. y2 is 0 minus y1, which is here, 0, over x2, 3, minus x1, 1. Well, that's going to be 0 over 2. And anything, 0 divided by anything is still 0. So my average rate of change there is 0. I think the easiest way to do this is to just plot the 2 points and draw the line and count down and over or up and over, and the slope is the average rate of change between the 2 points. Okay, so I'm going to speed this up a little bit, see if you can check your answers quickly. So now I want the x-intercept of graph B. Let me go get graph B. Okay, so now I've copied over graph B and the table for graph B. And again, I'm going to go through this fairly quickly. So the first thing it's asking for is what is the x-intercept, or what are the x-intercepts? Well, there's one there at -4, 0, and the other one is right here, the origin, 0, 0. X-intercept, where do they cross the x-axis? The vertex is the point at the top, which is the maximum, or the point at the bottom if it's opening up, or the minimum. That point is -2, 4. Sign of the leading coefficient. Remember, it's opening down, so that would be negative. And the vertex represents a minimum or maximum. Well, it's a negative a, so that's a highest point. Can never go any higher than this, so that is a maximum. Find f of negative 1. That means what is y when x is negative 1? So when x is negative 1, y is 3. And when x is negative 3, what is y? X is negative 3, y is 3. F of 2 equals negative 12. So if I went over here, I'd have to go way down here somewhere to negative 12. Predict the value for f of negative 6. Well, what they're saying here is our axis of symmetry is right here. And 2 is 1, 2, 3, 4 units from the vertex, or the axis of symmetry, I mean. So if I go 1, 2, 3, 4 units to the left of the axis of symmetry, I'm at negative 6. So I would say that f of negative 6 would be equal to f of 2 because this is symmetric. And that's my explanation. And I would say f of negative 6 is also going to be negative 12. Now it says on what intervals of the domain is the function depicted in the graph increasing. Okay, so let me move my graph down. I don't know if I'm ever going to use that table, but just in case. All right, get rid of that. Okay. So now it's saying, move that over a little right there. On what intervals of the domain x values is the function depicted by the graph increasing? Well, it's increasing here. It's increasing all the way up until we get to there. So that interval is coming from negative infinity, and it goes all the way up to when x is negative 2. On what interval of the domain is the function decreasing? Well, it's decreasing from my vertex to infinity. So it's decreasing from negative 2 to positive infinity. What is the average rate of change? Okay, so let me erase this. I'm not going to do the y2 minus y1 over x2 minus x1. So what I'm going to do is just simply use, let's get rid of this the other way. I'm going to use my graph, and I'm going to just simply use lines. So at the point x negative 5 is here, right here. When x is negative 5, y is negative 5. And to negative 4 is here. Well, if I drew a straight line there, what's its slope? Well, I went up 1, 2, 3, 4, 5, and over 1. So that's a slope of 5, or a average rate of change of 5. Now if I have the points negative 4, which is here, and negative 3, which is here, x values, remember. So now I'm going up 3 over 1, so my average rate of change is 3. Okay, now they're talking about the points negative 4 to negative 1. Well, negative 1 is here. Where am I on the graph? Well, that's right there. So to get from there to here on a straight line, I went up 1, 2, 3, and over 1, 2, 3. 3 over 3 is 1. And then finally, last points, negative 3, x value is right here on the graph here. And then I go to negative 1, and I go up to where it is on the graph right there. And if I drew a line to connect those, the slope is 0. Okay, so now it says, understanding the symmetry of quadratic functions and their graphs, look at the tables and row 5 in the chart. A. What patterns do you see in the tables of values you made next to graph A and graph B? So here are the two tables. Okay, so what patterns do you see? Well, this is increasing by 1, increasing by 1, increasing by 1. This is also increasing by 1. And what does the y value do? Decrease, 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 and then increase, increase, increase after it got to the vertex. And this one increased, 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 decreased, decreased, decreased. Okay, so that's that. All right, Now it says vertex and axis of symmetry. Look at rows 1 and 2 of the chart. So if I go back, they're talking about this, rows 1 and 2 of the chart. Right here, I've got some garbage in there. Let me move it. Just so we can read that, get rid of these points. That's better. So we're looking at rows 1 and 2 in the chart. So here and here. How can we know the x-coordinate of the vertex by looking at the x-coordinates of the zeros or any pair of symmetric points? Okay, so here are the zeros. Zeros are when y is 0. So here's 1, here's 3. Well, what do we know about this point here? What do we know? Can you see a pattern? Okay, from 1 to 3, what's in between it? What's the midpoint in between it? So the vertex is the same distance from the two x-intercepts. So 1, 2, 3. If this was 1 and this was 5, this would be 3. Distance of 2 from 1 to 3. 3 to 5 would be 2 as well. So same here. -4 to -2, we have to add 2. Add 2 to -2, and we're at 0. So the vertex is the midpoint x value of our x-intercepts. Understanding end behavior. Look at rows 3 and 4 of the chart. So we go back to rows 3 and 4 of the chart now, which is here. What happens to the y values of the functions as the x values increase to very large numbers? Okay, what happens to the y values is x gets really big or get really small. Okay, so knowing that the function is positive and has a minimum, when x values get really, really big, we're going to positive infinity. When we have a maximum and the sign of the leading coefficient is negative, then we are going to negative infinity. So the direction we're going is going to be our end behavior. Identifying intervals on which the function is increasing or decreasing. Look at row 6 in the chart. So let's look at row 6 in the chart. Get this out of the way. Row 6 in the chart is right here. This was infinity, I think. And this was 2, negative infinity to 2. Okay, just clean that up for you. So there the values are for 6. And let's go back and read the question. And it says, is it possible to determine the exact intervals that the quadratic function is increasing or decreasing just by looking at the graphs of the functions? Okay, and the answer is yes. If we have the vertex as well. Okay, computing average rate of change on an interval. Look at row 7 in the chart. Okay, I really don't like going back and forth like this, but anyway, here's row 7 in the chart, average rate of change. Explain why the average rate of change over the interval 1 to 3 of graph A was 0. Okay, well, graph A was here, intervals from 1 to 3. Well, it decreased -1 here, and it increased 1 there, and average means to add up all your changes and divide by that number. So -1 plus 1 is 1, or 0. So the average change was 0. It went down 1, but then it went back up 1, so the average rate of change is 0. Okay, so actually if I drew a horizontal line across here, remember what I said, slope is the same as average rate of change. So the slope of the line between these 2 points, the segment is 0. Okay, so the reason the average rate of change over the interval from 1 to 3 was 0 was because the y values for the x value 1 and the x value 3 were both the same. All right, so G says, how are finding the slope of a line and finding the average rate of change on an interval of a quadratic function similar, and how are they different? Okay, well, they're similar by using our formula y2 minus y1 over x2 minus x1, if you will. Okay, and if we use function notation, then it'd be f of our first value minus f of our second value divided by, that should be a b, f of our first value minus f of our second value divided by those values. So f of a is simply what is y when a is a certain number, and what is y when, so these are our y's and these are our x's. Okay, so they're the same because we're using this formula, rate of change, change in y over change in x. How are they different? Well, a linear function, a line goes on forever and ever and ever and never changes. But in a parabola, if I wanted to know the interval from here to here, then the slope here would be this steep value. But if I then wanted to know the value from here to here, then the slope has decreased and it's gone to there. If I wanted to know the slope from here to here, it is now turned and gone positive. So the rate of change between intervals on a parabola changes all the time, where the rate of change on a line, no matter where you choose it or how far you go, it is always going to be the same rate of change. Okay, so finding a unique quadratic function. Can you graph a quadratic function if you don't know the vertex? Can you graph a quadratic function if you only know the x-intercepts? Okay, if you don't know the vertex, can you graph a quadratic function if you don't know the vertex? Okay, so you need more than just the vertex to graph, but if you don't know the vertex, I would say it's possible that you could graph a function, but if they're just simply saying if I had a xy axis, coordinate plane, and I had some points already given to me, say I had these 2 points, 1 and 4, 1, 1, 0 and 4, 0, I don't know the vertex, I can't graph that parabola because the vertex could be here and it could curve over like this, or the vertex could be way up here and this function could go like this. But then I don't know what a is, so the parabola could go this way. So just knowing the vertex doesn't help. Not knowing the vertex doesn't help. And can you graph a quadratic function if you only know the x-intercepts? And the answer is no, and this is why. I can have infinitely many parabolas that go through 2 points on the x-axis. Okay, different vertices or vertexes and different a values, positive or negative. Remember that we need to know at least 2 points to define a unique line. Can you identify a unique quadratic function with just 2 points? Okay, well, I just kind of explained that. The answer is no, because the rate of change between 2 points is always changing. Your average rate of change is always changing, and just 2 points will never give us enough information to correctly graph a parabola. J says, what is the minimum number of points needed to identify a unique quadratic function? And the answer is 3. So if I had an axis xy and I told you that this point is 1, 0 and I told you that this point is 7, 0, then that's a distance of 6. And if I told you that the vertex was 1, 2, 3, 4, 5, 6, 7, so if I told you that the vertex was, it's got to be halfway between this, which is 1, 2, 3, 4, 5, 6, 1, 2, 3, so that'd be the point 4, comma, let's say 5. If I told you the vertex was 4, 5, 1, 2, 3, 4, up 5, okay, right there, then that is enough information to graph the parabola. You just draw a curve through here, back down, and it goes to negative infinity this way, it goes to negative infinity that way. So 3 distinct points, the vertex and 2 x-intercepts, we can graph a parabola. And they don't even have to be x-intercepts, they could have been these 2 points up here. As long as we had 2 points that were symmetric and the vertex, we can graph. Or what if we had the vertex and 2 on one side? Then we could also graph over here. So the vertex and 1 point would not be enough. Or would it? It might. Okay. Exploratory challenge 3. Below you see only one side of the graph of the quadratic function. Complete the graph by plotting 3 additional points of the quadratic function. Explain how you found these points and fill in the table to the right. So I'm going to start, I like going in order, so we're going to start from the left and we're going to work our way to the right on the x-axis, starting with the x value -3. The next x value is -2. Now I'm only choosing integers. There are also points in between, like here, but we would have to estimate what those are without knowing the exact point. So I'm using the corners of the grid to get integers. So the next point is -1, x value. The next x value is the origin 0. So we're increasing by increments of 1, so I'm going to continue doing that. And then now when we go down the other side, this is our vertex here. And this y value was -6. And at -2 we were at -1. And at -1 we're at 2. At 0 we're up at 3, and that's our vertex. And so remember, if we have a vertex and points on one side, the y values will match on the other. So if this is 2, this is 2. If this is -1, this is -1. And if this is -6, this is -6, provided we do the same change over the x interval. So now I'm going to just plot these points. 1, 2 is here. 2, -1 is here. And 3, -6 is down here. And if I connect those dots, we have the other half of this parabola. What are the coordinates of the x-intercepts? Okay, so now we need this graph to answer these questions. Okay, so here's the graph. What are the coordinates of the x-intercepts? Well, here's one x-intercept right here, and here's one x-intercept right here. Okay, so now that I look at this, these are in between. It'd be an approximation or an estimate, but I'm going to show you something. It might be a little bit beyond what you're doing right now, but it never hurts to go ahead. Remember that our axis of symmetry, our vertical line, is x equals -b over 2a. Well, that vertical line is on the y-axis, so that's x equals 0. So if I plug in 0 for x and say that that equals -b over 2a, well, what can we gather from that? What fraction will give us a 0 value? Well, it's when the numerator is 0. So if I have the function ax squared plus bx plus c, and my b is 0, then this is not there. So now I've narrowed it down to f of x equals ax squared plus c. Well, what is my c? C is my y-intercept, which is 3. So now I have f of x equals ax. Running out of room here, so I'm sloppy. F of x equals ax. F of x equals ax squared plus 3. All right. So now all I need to know is what a is. But I have some x values, so let's use them. So I prefer using positive numbers. So when x is 2, y was negative 1. So f of 2, or I don't want to use the f of, I want to use the y value. When y is negative 1, right here, x was 2, equals a times 2 squared plus 3. Well, if I subtract 3 from both sides, then I get negative 4 equals 2 squared, which is 4 times a. Okay, so if I divide both sides by 4, then a equals negative 1. And so now I have my function. Now I know that it's f of x equals negative x squared plus 3. So I was able to find the function's value by using the vertex and points. So now I know that the function negative x squared plus 3, and so now I want to know what the coordinates of the x-intercepts are. Well, that is when y is 0. So 0 equals negative x squared plus 3. In order to solve this, I can move everything over to the other side so I don't have a negative leading coefficient. So if I add x squared to the left and right, it goes over here. And if I subtract 3 over to the other side, now I have the function switched, x squared minus 3, just to find values. And then, or here, let's do it this way. I don't want to confuse you. Subtract 3 from both sides. We're solving for x. Negative 3 equals negative x squared. So if negative 3 equals negative x squared, then x squared equals 3. Take the square root of both sides, and we get x equals plus or minus the square root of 3. So this value right here is the square root of 3, comma, something. And then the other point is the square root of negative 3, comma, something. So the coordinates of the x-intercepts are negative 3, comma, 0, or square root of 3, comma, 0, and negative square root of 3, comma, 0. Okay, that was a little tricky. B, what are the coordinates of the y-intercept? Well, the y-intercept is right here, and it's the point 0, comma, 3. It's also the vertex. What are the coordinates of the vertex? Well, I just said 0, 3. Is it a minimum or maximum? It's at the top. A is negative. It is a max. If we knew the equation of the curve, what would the sign of the leading coefficient be? It's opening down, so it'd be negative a. And E says verify the average rate of change for the intervals negative 3 to negative 2. So that's here, this point here, negative 3, negative 6, and negative 2, comma 1. So go up 1, 2, 3, 4, 5 over 1. The average rate of change is 5 over 1, or 5. Based on your answer to row 6, in the table for Exploratory Challenge 2, what interval would have an average rate of change of negative 5? Explain. Okay, well, if the average rate of change from negative 3 to negative 2 was a positive 5, we went up 5 over 1, well, we're going to go down 5 over 1 between the intervals of 2 and 3. That is the end of a very long lesson 8. Review the lesson summary, take a break, and then go do your problem set.